and the points don't matter. We've got a pretty distinguished group here, and the way we're going to work it is we have two mic runners. Jenny, raise your hand, raise the mic, okay, and the other one over here. And then for people that ask a question that's deemed appropriate, Jacqueline here actually has a gift card for, what's that? Oh, Amazon. Oops, sorry about that.
That's actually useful as opposed to the empty.
Anyway, so we get started, my name's Steve Pawlowski. I'm the moderator. I work in our data center group. Leading team that looks at new technologies to integrated the server and embedded space. To my right here is Belly Katana. Belly is the chief architect for the Atom. I'll tell you what. I'll go through here so that So to finish introducing Belly, he's the chief architect of our Atom and our Quark microprocessor product lines. So he has a lot of influence in the direction that we're going. Mark Doran. Mark, please raise your hand. So Mark is what I'd say a newly minted Intel fellow, I think as of last year. He works in our software and solutions group, and he's the chief software architect for our system software. We've been working together for 20-some years, I think. Link Job. Link also is a new Intel fellow who came to us recently from, what company was it?
Scientific Monitoring.
Okay, I'm sorry, I didn't know that. Link is an analytics. He does analytics, and he's one of our chief analytics architects in our embedded solutions group. Sometime I suggest that if you get the chance, sit down and talk to him, because the kind of work they do and the impact it's already had in terms of his big data application has been pretty extraordinary. And every time I get in an airplane, I'm kind of glad that Link's around and he's doing the work that he's doing. Per Hammerlin. Per, raise your hand. So Per is one of our chief processor architects. He actually was the chief architect for Haswell, and he's working on our next generation processors that are really geared toward more, I think, the mobile space. Okay. Hong Zheng, our key media architecture architect. His media capabilities are in the next generation Haswell product. He's going to finish here, and then he's going to go do a media tour in Asia to announce the new architecture and its capabilities there. So we're happy to have him here. Tiki Thacker. I hate to embarrass Tiki, but when I started graduate school in 1984, Tiki was my first professor. And I always wanted him to work for me someday, and he hasn't yet. But when he does, he's going to feel the wrath of 1984. So, anyway, Tiki's an Intel fellow. He's had a pretty distinguished career, not only in academia, but in Sequence Systems before coming to Intel. And he works in our mobility space as chief architect, one of our chief mobility architects. Belly, we already introduced Belly, so it doesn't need any more introduction. Rich Ulig, whenever you see our virtualization technology, he's the guy. He's worked at Intel Labs, but he has a unique relationship with the product group. Rich is the kind of guy that comes up with an idea and then works with the product team to deliver it. And he's one of our most critical system architects that we have. He's been on sabbatical. We have an 8-week sabbatical every 7 years, and he just got back, and I'm really glad he's back. I didn't know he was back until today, and I'm glad he is, because I have a lot of work for him to do. Knut Grimtrud. Knut's been around for he's been at many of the, he's even moderated these fellows' live sessions. He's our chief architect in the storage division. He's what's taught me everything I needed to know about disk drive and disk drive interfaces. And he's continuing on as disk drives and the whole non-volatile memory ecosystem starts to evolve. And then last but not least is Al Guerra. Al was the chief architect for IBM Blue Gene Q. He came to us as an Intel fellow, and he's leading our research in exascale in the next generation of high-performance computing, which we call the exascale systems, that should start deploying in the 18 to 19 timeframe. And we've been given a significant challenge in the industry of doing it in 20 picojoules per operation, which is almost unheard of, but we figured if anybody could solve the problem, Al and everybody up here can do it. So with that, we'll take questions. Please raise your hands. The mic runners will come. Yeah, and I get actually, we do have, first question. This gentleman actually was in the Haswell conversation we had yesterday. And and everybody was asking system questions, and unfortunately on his system questions I said, stop, this is really a Haswell conversation. Come to Fellows Live and Uncensored and you will be the first question, guys. So
thank you, Mr. I'm Satoshi from NC. My question is about connectivity between processors. Currently, the massive power processing in data center is more and more important thing, and then this processing is one of the key applications with Atom or the Xeon. And then, but then for the connectivity, there are a couple of solutions like QPI and that, and also the performance in terms of the connectivity, the latency and the throughput is an important aspect, and then we need to improve the performance further. For that, we have a couple of solutions like QPI and user mode driver, RDMA, and so on. So, and also the couple of emerging technologies, and also Intel is acquired a couple of cutting-edge network companies. So I'd like to ask you your prospect in the future network architecture, the extension in the core.
Al, I hate to put you on the spot, but I think this is right up your alley.
Okay, so let me try and start from the HPC side of that. So obviously you've seen the visible acquisitions that we've done in terms of acquiring some resources in this space, in the fabric space. So what we're trying to do is really focus first on bringing those resources. We're going to apply them broadly over many different market segments, but we're looking to HPC in a way to sort of drive that technology and to sort of really, because HPC, all of the things that you mentioned in terms of performance and latency and all of these things in HPC, these have been historic problems for a long time, and the problems are even more severe. And as we go forward, we see that the focus on that needs to increase. And so as we go forward, we realize that both on our processors and in the fabric, and we need to start thinking about these holistically, not as separate things, but really together. And that's really why we did some of that. And so initially, you'll see things coming out that are we wanted to apply over the broad market segment, but we'll also be keeping a very close eye and really making sure that in the HPC sector we're letting it drive some of those capabilities. So I hope I answered your question.
Okay, right here.
Hi, I'm Mike Pryor. I work at Kodak Alaris, retool Kodak. And we're working on a USB 3 peripheral. And we're having significant problems with Haswell's C1 stepping. It turns out the quote-unquote insignificant problem is not so insignificant for us. It causes disconnects that we can't reconnect, even if you power down the scanner. And I've talked a little bit with Dell, but I'd like to find out what Intel has considered doing as basically a way of looking at other alternatives versus waiting for C2 stepping. Our problem is we're going to have to tell customers what to use or not to use. And at this point, we may have to tell them, avoid Haswell, because it's going to break. So I'm just curious if there's other workarounds besides new chip.
Well,
So this work. Let's since I don't know what your problem is, it's really hard to comment. So if you could just meet with me up here right after this, and we can talk about it.
yeah, and typically, if you want to, the field usually is pretty averse to what works and what doesn't work and making recommendations. I assume that you've actually talked to them.
Yeah, all we're hearing so far is new chipset. That's not a good solution for anything.
Oh, okay, yeah.
And I
Well,
ran into Gigabyte downstairs who had some other alternative they're looking at.
okay, yeah, then perhaps if you could meet up with Per afterwards, it'd be great. David, I'm going to avoid you to the last minute. I'm sorry. I don't want another question about memcaps on
It's
you.
a good one.
So, yeah, I'm sure it is. Okay. Right here. Jane? Oh, which one did you pick? Okay.
Is on the dual socket server space, how many cores, as the core count increases, do you guys believe we should go to single socket instead of staying on a dual socket, many cores?
And everybody's looking at me.
I can take.
I can answer answer too, so go ahead.
Maybe I'll give the wrong answer. You can correct me. It's very customer dependent and workload dependent. So there are a lot of applications that have the way you can arrange the memory access and everything so that having 2 sockets with that extra memory bandwidth makes a lot of sense. There is also some OEMs that really like the upgrade part of it. They will really sell populated with just one CPU system, so customers can go and populate the second socket later. So there are aspects like that are sort of not technical, if you will. They're business requirements we take into account. But for certain application and workload, it really makes sense to go to a single socket. And we're looking at when should we play that trick and in what segments going forward. So if you keep coming to IDF, you'll see it here.
Yeah, Per's answer is spot on. When we first started adding more cores to our sockets, we were told by our customers, hey, 8 threads is going to be the max, software can't take advantage of that. And, like anything else, as you start to build those systems and people start taking advantage of them, we're seeing more and more workloads that can actually take advantage of a greater number of threads and cores. So and that doesn't mean that those workloads are significant, but those workloads do represent market segments where the margins on those products are actually quite attractive. So, we're going to continue down the path of, adding cores when it depends on the workload, and at some point in time when we get to that limit, and right now that limit I don't see happening on a single socket for some time to come, we'll transition to that point.
Point I guess I could add in the virtualization space is that with virtualization of servers, we're able to consolidate multiple OSs. That's one of the ways to get around the thread limit that traditionally has been a concern, is that how many CPUs can you support in a platform that effectively utilized.
Yeah. Okay.
Lance Leventhal, VHCA Newsletter. What do you see as the role of software-defined networking?
Go ahead and try it. And I'm trying to. I kind of want some questions to let some of these other guys talk. Go ahead.
Well, SDN really, in a sense, is kind of an evolution of what's been going on in the virtualized data center. With CPU virtualization, we've been able to solve the problem of consolidating load onto a single server, but we still haven't really achieved the ultimate goal of the IT folks, which is to get really rapid provisioning of services and multi-tier applications into the data center. And that requires a virtualization of the network itself. So getting beyond the physical configuration and topology of the data center network, and being able to move into a space where you can have a sort of a virtual overlay of the network that can be the way to deploy a service. And so SDN really just is kind of an evolution of what's been happening in the data center for a while now, and extending to networking and storage as further resources that are virtualized and easily provisionable.
And it allows the customers to provide differentiation in the overall management stack, which in a lot of cases they don't have that ability to do.
Exactly.
Does that help? Okay, next.
Yeah. Can you explain the reasons for moving DisplayPort into the processor?
Ellie. Is that one you'd like to take? Or?
It might be a
I could explain the reasons for moving DisplayPort in the processor.
That's Tiki.
There you go, Tiki.
I think are you referring to Haswell or?
Haswell.
It was the system partition we had between the chipset and the CPU in Sandy Ridge and Ivy Bridge. It made a lot of sense to do that for where we put certain components, audio, and how we wanted to deal with some of the high voltage IOs that are involved. So for us, when the standards were a little bit more clear in the Haswell timeframe, we could actually just take the cleanup step if you want, or simplification of moving it onto the CPU only, and not sort of route display traffic through from the CPU to the chipset and out. So I view it as a cost saving and sort of a simplification of the system partition.
Tiki, do you want to add anything?
SoC, there is only one place to put only SoC.
So I want to invite you people to Per Hammerlund live and uncensored. So next question.
Of course, on that one, there's also power saving too. There's microcontrollers and microprocessors, and actually display engine, display port is in place. Makes sense that way.
Okay, next question.
So you've talked a lot about the disaggregation of the data center, moving to, if you will, disaggregated CPUs, disaggregated memory, pools of memory, pools of CPU, pools of storage. How soon is it before Intel is really truly in a position to support that? And by support that, I mean I can buy parts from you, build this system so that I have the pooled memory controller, the disaggregated memory, the disaggregated, the storage. That's easy, that exists today. Other portions of this don't exist. The high-speed optical interconnects, the high-speed internet connects to build the fabric and mesh all this together don't exist today. You're putting out this vision. When do you see this vision being achievable, physically touchable?
Well, number one, you won't buy it from us. You'll buy it from our OEMs or distributor, through the channel. What we've shown in marketing literature is the first elements of that architecture you'll see in the 15 time frame. And as we start to roll out silicon photonics and we have the pooled memory controllers and things like that, which are getting on the roadmap now, which means that we're going to see those in the next few years. Late 15, 16, 17, you'll start to see more and more of those capabilities being available that'll be offered from our standard the vendors that sell our products. Next.
I guess my question may be related to the one he just had. It was just a comment on your announcement, 3 or 4 years ago, of your nanophotonics or whatever you call it over your CMOS and your 60-core, 80-core type processes. It seems to me that those are really going to offer revolutionary type of opportunities there, provided that the software code is written in appropriate parallel, similar to what we've heard to your existing products, but even associated code. I was just wondering what y'all's plans are in that regard. Is that all going to be left to the, shall we say, your OEMs? Or is Intel going to provide any type of help there?
So let me see if I understand the question. The question is, are we providing revolutionary code to run on these platforms, or?
No. The question really has to do with when these processors are going to be available. And I know you have data on your website to help people in terms of parallelizing code, I guess you call it.
We have products available today. That's the Xeon Phi. So we announced, when the 1680 core, those were the research prototypes that have actually led to the Xeon Phi product line, of which there are tools, parallelizers, thread checkers, and things like that available for that. Are you thinking something beyond that, or?
I was thinking a bit beyond that, but never mind. That's fine.
Okay. Yes, I'm depending on these guys to tell me who they're giving the mic to. Okay, over here.
Yes, there are no Intel fellows from the manufacturing side. My question really is to manufacturing. If I look at your manufacturing versus capacity of foundries, the delta has increased at the highest level since at least a decade, in the past decade or so. I was wondering, since foundries have access to the leading universities as well, why have you been able to have a steal a march on your competitors in material science advancement, things like high-K, metal gate, and FinFET more recently? And is that something that we could, this magic source of Intel can be maintained over time?
Since none of us up here are really material science experts or related to that capability. What's that?
We should add Kalen.
Should add Kalen or Mark Bohr here. Why don't you just send me your question, and I'll go ahead and give it vector to the appropriate person that can give you an answer.
But I think we can also repeat what I think BK and Renee said yesterday, right? That first of all, I think it's a lot of hard work. I don't understand all of what they do for sure, but there is a lot of hard work and focus in those teams. And I think when we look forward to your question whether we can maintain it, right now we don't see a reason to think that it will taper off.
I misunderstood the question. I thought he was asking if we were working closely in growing the next generation of material scientists. So.
It really is that the textbook are the same on material science for everybody, I assume, and access to leading universities are the same. And FinFET has been out of Berkeley for at least a decade, right? But you were the first to implement FinFET, and the closest guy is scrambling hard to do the first iteration of FinFET. So it's not the access to the leading edge science breakthrough that matter. It's when you commercialize and make it production worthy. That's the secret sauce.
Yes.
I think we have enough secret appendices for all those books.
Yeah.
That they get to read.
Okay, next question.
Hello, Jack Clark from the Register. As Intel starts to churn out more and more different SKUs from chips, like 13 atoms last week with different capabilities in compute or networking or storage, I was wondering what stands in the way of giving a higher variance from SKU to SKU of the same common architecture, and what you're working on there for allowing you to make that even wider.
Anybody?
You're the moderator.
I'm the moderator? Well, everybody, I'm also the guy that's probably going to catch hell afterwards. Why did you pick me for that question? Han, why don't you?
I can comment from the architecture from a graphics and multimedia side. We do have to address the broad market with common architecture. One key reason for that is software consistency and software development has been the major hurdle for us to deliver time-to-market solution and also scalable solution. Have a common architecture across a broad range of segment allows us to deliver the total solution from hardware and software. And for that, we are looking at the core base building block for the scalable architecture. And you see from Haswell, we do deliver GT1, GT2, GT3 with EDRAM. Definitely clearly cover a pretty broad range of the segment. We also deliver the baseline Gen 7 IP into the Atrium, which again gives us easy access to the software we have stabilized on the previous generation core. So software stability clearly a major motivation for us to deliver the solution across a broad segments.
Jeff, did that answer your question? Okay. Next.
Hi. I have two questions that are very related. So I come from the gaming side of, not the server side of the world. My first question is, as the OEMs are using mobile pieces more and more in desktop devices, especially all-in-one machines like the iMac and all the other OEMs have similar devices, is the desktop line of CPUs at some stages going to become part of the mobile line, or are you going to keep developing? And the second question, which is related, is with the Iris Pro, are you guys in the long term targeting to compete at the high end of the graphics, or is your goal just to be able to make competitive mobile graphics devices?
So maybe if I take the desktop. So I think we see it's a little bit like Moore's law is dead. Everybody thinks that desktop sales are dead too. They're actually still a fairly sizable fraction. They're a smaller fraction now because the growth in the other segments has been much higher. So we will continue building SKUs of the architecture that are targeted specifically at desktop, that have good PCA connection and so on, so you can hook up your favorite discrete graphics. We see those as important platforms that we will continue optimizing for. So they will be there as far as I can see into the future. And maybe Hong, you can take the...
So for the second question regarding Iris Pro, clearly we continue looking at the scalability as on the previous question to address the broader capability. And there's, of course, the limit of the socket power, how much power can provide a single socket. So we're providing solutions still in the microprocessor we have in our offering. So we do not have a discrete market. Therefore, there's no 200-watt solution in there. So for that, you're right that the mobile gaming market is clear, very spot hit with the solution. So we look at our solution at the 65-watt platform, we can deliver a very competitive solution, deliver a smaller form factor and also a better cost structure for our customer. So we can continue to expand in that space, but upper limit is still the socket power.
Okay, next.
So can you comment on Intel's software strategy for high-performance computing, particularly in the high end for petascale class systems and in the future exascale class systems? Just what it takes to enable the usage of the effective usage of that hardware.
So I will leave it to you and Mark to arm wrestle each other for that answer.
Okay. So, well, clearly that's one of the huge challenges. And I guess the first thing I'd say is when we look at this problem, it's a combined problem. It's not just a software or only a hardware problem. We're really trying to address the architectures that we go forward with when we think of exascale, both from a hardware and a software perspective. So truly that sort of co-design type of thing where we realize that, you know, hardware architecture elements that can't be exploited by software don't make any sense. So really these two things are very tightly coupled. And so what are we doing specifically? Well, so that's part of our thought and a part of our real architecture development process is to be thinking about that right up front. The next part of it is we realize that to explore some of this space, we need to be able to develop and to deliver reference designs to the community, also on the software space, not only in the hardware space, but also in the software space. And as we go forward, we're looking at even more of that, where we start to enable higher levels of the software stack and perhaps even all the way end to end, in terms of really giving the community sort of more of a reference design software stack so that as an OEMs don't have to deliver and develop the entire OEM software stack. That's the entire end-to-end software stack. That's becoming really prohibitive. So we're looking to trying to help out in that space by trying to give something so that you can specialize in whether it's a messaging layer, OS layer, whatever it might be, but that the other pieces might be there to sort of take and reuse.
Now, can I add something? Did you want to add something, Mark?
That pretty much covered most of what I was going to say. I mean, the idea of trying to ensure that there's a set of modular components in the software that complement the hardware designs that we've got, so that you can, cherry pick the pieces that are good enough in the reference designs to actually create something where you're adding value in your own specialization. That kind of shake and bake type recipe is something that we like to be able to make sure that everybody has an opportunity to participate in.
And now to add one more thing, if you were in BK and Renee's the keynote yesterday where they announced the OHSU collaboration on personal health care, that's actually what we call an exascale lab. And the idea there is to understand the workloads and the emerging workloads and be able to figure out ways to build machines that are actually a little more efficient in terms of exercising those algorithms. When the HPC guys publish their top 500 number, those are pretty impressive numbers, but when you run real applications, they're probably on the order of 10 to 15% efficient now, wouldn't you say? We want to get it higher, and so we've established things like that in order to understand how the applications work and be able to adjust our architectures accordingly. Next. Okay.
From an ISA perspective, for desktops and workstations and servers, x86 clearly has a very large stronghold. In the mobile space, if you look at the marketplace, most of the devices today are running the ARM architecture, and a large amount of the software ecosystem is dependent on ARM. Do we believe that with the Intel bridging technology that was talked about, that we're getting to a place in mobile where ISA really doesn't matter anymore?
Vicky, I think that's a you and Belly question.
I think it's too early to say, whether the ISA really doesn't matter or not. I think so. As far as the strategy goes, we continue to push for, making things that run natively on our instruction set, work as well as possible. And then for the cases where we have to run someone else's ISA on our devices, we look at supporting those things too, right? I think it's just too early to jump to a conclusion on that.
I'd like to add that a lot of the code is interpreted, as you're pointing it out, but even then, the code, the interpreter running on Intel architecture actually works much better than on our competition. The other places, things like a lot of the tuning, for example, HTML5 is being done on Intel architecture. So all of those things translate really nicely. If you look at JavaScript, it works better on Intel architecture. And there's credible proof points now. You can run, JavaScript benchmarks and see Intel versus our competition, and you'll see a 2x difference in some of the current generation devices. So, from my perspective, it does matter because it delivers better user experience today.
Okay, next question. Okay.
I have a question about Xeon Phi. So today's usage models for Xeon Phi, looking at it being used as an offload processor or co-processor to the main Xeon. In the future, do you see usage models where the Xeon Phi becomes the host processor, or a mic architecture becomes a beefier Xeon Phi, with full Xeon cores becoming the future server architecture?
You want me to do that?
I'm trying to remember how much we said about the first part of that question. The second part of that, I can easily get.
Well, this is all about, so this is mainly the question was about hosted versus accelerator?
Yeah.
So the answer is yes. Yeah, the answer is yes. By the way, this gentleman's been holding his hand up for a while, so we may want to get a microphone close to him. Okay.
He's been holding his up longer now.
Okay.
Another David.
Yeah, David. I'm saving David for last. Number one, I want to give him 30 seconds for his question. Otherwise, it'll take the remaining 29 minutes. And then we can get a quick response.
I'm Jim Handy. I'm a memory chip analyst, and so I care about memory, and that's about it. I wanted to ask actually two questions in one. One is, what is Intel's long-term vision for the hybrid memory cube? And then the other is, what do you see in the long term for NAND flash in the data center? How is that going to be used? Is it going to be memory, kind of like what you started out doing with Braidwood, or is it going to be storage and continue to be presented like hard drives are?
If you don't mind my asking, is there any reason you picked in particular hybrid memory cube?
2 years ago, it was given the spotlight at the Intel Developer Forum.
Interesting. So there is so whether it happens to be hybrid memory cube or high bandwidth memory, whatever the HBM, whatever it happens to be, there is a role in certain segments for stack memory. Okay. Now, whether that has its own logic die and communicates logically, or whether you have to put it on a substrate in order to be able to communicate with the processor, we haven't determined yet. We're still working out that analysis. But I think there is a role there. Do you want to take the NAND question?
The flash question. Is this one on? All right. The flash question, and thank you very much for asking a storage-related question. I was kind of feeling like I was at a dance, and nobody was like asking me out, So thanks for that.
I have that problem all the time.
So I think that for NAND flash, the usage is primarily going to be storage rather than memory. And it really has mostly to do with the characteristics of NAND and its structure. It is not a write-in-place memory. It is not a byte-writable memory. And so by its very nature, it's kind of a block type of store. And block store is really better suited for storage than it is for memory. Also, it's the latencies and so on make it more storage-like than memory-like. And so I think NAND flash has a really bright future in data centers, and I think where it's primarily going to shine best is for storage. Now, there are some memory-like augmentation that we're seeing. For example, NAND-backed DRAM, which are these NVDIMMs, which is really, just on a power fail, doing a quick copy of the contents of the DRAM to the NAND flash and then restoring it on the restart, so that you can emulate non-volatile memory that has memory-like access attributes. And so that is a kind of an interesting area. Hasn't really played out well, but it seems pretty interesting to me. But I think the bulk of the NAND flash that will be sold in enterprise will probably be block storage.
Okay, next question.
So I would like to go back to the Xeon and Xeon Phi question. Host and Xeon Phi as an accelerator or coprocessor. So currently we use PCIe Express for the communication, which is we think is a bottleneck. Does Intel consider to put the Xeon Phi and Xeon in the same die? So in the near future? So if so, how difficult we can really integrate this Xeon processor and Xeon Phi together?
So, there are many things that are still being considered. Of course, we've already sort of locked down what we're going to do on the next generation and getting closer on the next. But as you go further out, the type of things that you're talking about are always, we revisit them every time. Do we want to put both of these things together to handle strong single thread and to have highly parallel, energy efficient parallel threads? Right now, I would say that, Steve already said that we're talking about self-hosted solutions for the next generation, so he's let that. So I can tell you that...
No, I just said yes.
Yes, okay, you didn't say that. So in any case, the question of the role that a big core plays and a Xeon Phi core plays, I think that we will see some of that changing over time. I think that the bottleneck between those is going to change. We're not going to have the same kind of constraints that we have in the future. We recognize that this is really one of the difficulties to scaling codes and making codes, porting codes and even getting codes to run efficiently. That is difficult. So we're trying to address that. And as we go forward, we're also looking at the space that you've talked about, which is doing more heterogeneous type of solutions. But we're not committing to any of those right now.
Okay, next.
So I've had a couple of related questions about future or unintended uses of specific Intel technologies. So Intel VT was very much designed for full system virtualization and acceleration, but now we're moving so much in the direction of application containerization, things like Docker, or in Chrome and Chrome OS, application and browser sandboxing. I'm wondering what opportunities you see for Intel to improve sandboxing technology for lighter weight or container style sandboxes. And related to that, with the announcement of Quark yesterday, when Atom was first announced, it was intended just for embedded, and now we see ARM servers and microservers and similar. What possibilities do you see for Quark, not just for tiny embedded devices and the Internet of Things, but seeing 1,000 Quark servers and similar?
So, Rich, I think you're probably the best to answer the first part.
Sure, I'll give it a shot. Kind of an interesting historical fact is that when we first started looking at VT architecture, it wasn't for full system virtualization, it was for security and for building isolation technology. When we architected it, we decided that wouldn't be wise to focus just on that application, and we did generalize it and took a page from some sort of historical mainframe design and decided let's build we're going to add a new mode to the processor, let's build something that's very general purpose and flexible, and let's go with the strategy of driving it across the segments over time. It found its initial use in servers, and that's where I suppose the questioner recognized that full system virtualization has been the first successful application. But we are intentionally implementing it in the client segments, and it's also rolling out in Atom as well. Ellie, earlier today talked about when VT features are arriving in Silvermont and to what extent. And so we do see security applications and building sandboxes for secure code and trustable code as being one of the key applications. One of the challenges we've identified with that is now we've got a couple of different competing uses for the technology. Sometimes they want to coexist on the same platform. So we have this problem of coexistence of hypervisors, one that may want to do full system virtualization, another that's providing security and isolation. And we have been investigating technologies and approaches to dealing with that. One of them is to support nested virtualization, that is the ability to run a hypervisor or some code that needs to use VT above another hypervisor or VMM. And one of the features that goes to that is called VMCS shadowing that does take out some of the overheads for that. It does come with a cost, but if you want both capabilities, we are looking at ways to bring them to the same platform.
Bill, second.
Yeah, as far as Quark usage in servers, in a many core environment, it's not something that we've really looked at yet. But the key there is when there's some kind of a breakthrough on some particular vector. In this case, it's efficiency as well as just raw power consumption. Right? It just opens up a bunch of possibilities. Right now, as BK said in his keynote, we're looking at IoT and wearables, things like that, as the main places where we want to use Quark. But going forward, we'll look at other things too.
And if I can add one thing, the 1,000 chip. When I hear 1,000 cores per chip, I worry about how we're going to feed it. And even if they happen to be low-end cores, they're going to demand a certain amount of memory bandwidth and a certain amount of I/O in order to be able to take advantage of those. So. Certainly, I think it's going to be a long time before we see something like that, as long as we can maintain the memory and I/O trajectory to be able to handle that. Stack DRAM is not the answer. Sorry.
Okay, this is Rick Michlewski from the Register.
Rick finally got the mic. That's great. Thanks.
Quick question. As you know, obviously, a lot of SoC vendors and IP designers are talking a lot about heterogeneous computing these days. CPU, GPU, shared memory stuff. Haven't heard anything from you guys about that at SoC level, and you're conspicuously absent, obviously, from the HSA Foundation. So I was wondering if you have any comments on that and what your thoughts are.
You want to talk about it from the technology side, or? Okay. Go ahead.
Let me start from the clearly the microprocessor and the graphics processor collaboration has been clearly a path, particularly when we add much more compute capability on the graphics processing unit. So there is multiple level of collaboration. The first level is to share some memory, and even today we have capability to do something called zero copy. So when you have operational data, the large amount of data, particularly when we deal with the pixels, just moving the pixel back and forth from two operation domain is just waste of resource and time. So that is handled today. But moving forward, clearly, having a common address space and a common way to address data, reduce the burden for programmer to move to a different programming is a very good objective to achieve. It's not just the hardware, but the hardware and software, even in the OS space. So Intel is not absolutely action, clearly.
Quick thing that I'd add to that is we did actually just in the last couple of weeks publish the specification for shared virtual memory support. It's under the BTD spec, it's our IOMMU architecture. So there are architectural details there that are available that you can look up.
But in terms of the standards question, we get inundated by, hey, we've got this standard association and that standard association. And we, as a corporation, evaluate where do we want to participate, where do we want to put our resources, because we don't have an infinite amount of resources to be able to apply to it. And we're constantly looking at when does it make sense, to either be the leader for the standard or when we want to be, get engaged with the standard. And this is just one that we're still having those conversations. Sorry, they'll get you the mic. Okay.
Hi, thank you for taking my question. So it looks like going forward, a lot of the volume growth areas are going to be related to the small core, the Atom core, everything from phones to tablets to even microservers. And you mentioned that Haswell is lead architect and they're working on Atom. So
I didn't say that. I said he was working on. Okay. Anyway.
But the point is, where do you see the big core, and how do you see the relationship between big core and small core going forward? I know that a lot of the PR stuff is that they're on the same level. Is that true from like a pure design and staff resources standpoint, or is it? I guess how do you guys view those two cores internally?
Let me take that one.
Please.
Yes, Ashraf, as I said in my session, right, our strategy right now is not to constrain either one of those microarchitectures. As we understand very well what the the operating ranges need to be for the microarchitectures, and then you get some of the additional benefits from the process side in terms of targeting, right? So we don't really need to see a need to decide that ourselves. We want our customers to decide where they want to see our product lines evolve to. We certainly don't want to get into a situation where we want to get complacent in certain segments where we are, leaders. So we watch for that. But otherwise, it's as an architect on the add-on line, I haven't been told to cap the upper end scalability of Atom, and same thing with the core line. My counterparts haven't been told something on the other end of the scaling range either. So it's we have the support system today within the company to evolve these microarchitectures accordingly, right? So we let the market decide.
And next.
Tommy Beth from Spire. I'd like to be unfashionable and talk about your large server Xeons. We're seeing some fantastic results with the Ivy Bridge ones. We're currently building a new product around. We're seeing such good results with so many cores that we're now finding the I/O is a bottleneck, and the amount of memory and everything. What plans do you have as you're producing all this extra processing power to release the I/O bottleneck on your high-end products?
No, can't look the other way. I'm going to feel like the plumber's law here at the bottom of the hill. That's okay. Obviously, I can't tell you what we currently have planned because a lot of these are in development, and I can't pre-announce any kind of products in any way, shape, or form. But all I can say is, we are aware of the issue, and as we add more cores, as I mentioned before, it's not only I/O, but it's also memory, because we have a lot of customers that say our problems are memory bound, and what are you doing to address those? And there are solutions that are out there working with the industry, as well as new technologies that we're bringing to bear. And a year from now, when we announce the next generation server, I think you'll see some of those things. So I guess it's good advertisement to come next year. Next. Yeah, and then this gentleman's been asking for Mike down here. Okay, go ahead, I'm sorry.
Karim Khan, I'm from the Cisco guy, and our friends over at Lighter Graph and you broke the world working for data mining and semantic data. So my question is, what are you going to do to leapfrog with your hardware like the yellow phones and the SSD infrastructure you have to allow massively multi-user distributed processing in microseconds, hundreds of microseconds level? And what's your play in that space? Because somebody's got to do it. The guys who are doing OpenStack stuff and their plays like that, Swift are waiting for vertical integration.
So this is really more of an analytics question?
Well, it's more about what you can do with hardware and do distributed processing across networks with your hardware, SSDs.
You don't want to?
I'll start this, and some other people can add to it. Yes, we're seeing a business process transformation, and that transformation is to change from the focus of gathering and collecting data from contributed devices to the focus of gaining insight from the data. And that's where you're talking about the data mining and analytics. How are we going to do it? And in Intel, we're actually looking at the options of distributing the intelligence among different devices from the edge to the cloud. And I think there, with the Intel architecture, which spans from the cloud to the device, and we're trying to maximize the performance and to make the best use of the Intel architecture.
Yeah, I think Link's right. I think that we're going to be moving compute closer to where the storage is. As an example, the National Cancer Institute has said that they have roughly about 2.5 petabytes worth of genomic data. If we were to transfer that over a 10 gig link, it would take a month with no errors across the length, and probably close to 500 to 750 kilowatts of energy just to do the data transfer. So I think going forward, as we look at larger data sets, just with the architectures will be distributed. We'll be moving compute closer to storage because it takes more energy to move bits than it does to actually compute them. Next.
Are benchmarks meaningful or benchmarks marketing?
Okay.
Or neither.
I think the benchmarks are a good indicator of, depending on the benchmark, they can be good indicators of what the users may experience. There's a set of benchmarks now being developed, at least on the tablet side, that are getting away from dry stones. And how much useful those dry stones were, as you can measure them. I mean, it's worthless, right? So, but some of the benchmarks that are being developed, like Touch Expert or Web Expert, and even on the Windows side, the sysmarks were, indicators of user experience. And I think those are meaningful benchmarks, and they tell the user some value you're going to get out of a new system.
Okay, next.
In your introductory comment, I thought you mentioned a high-performance computing project involving picowatt power consumption. Did I understand you correctly, and can you elaborate on that?
The target for exascale computing systems is an exaflop, which is 10 to the 18 flops, at a 20 megawatt power envelope, which if you translate that down, that says the average power per operation for the entire system is 20 picojoules per operation. That's a pretty aggressive target, and that's why Al and a lot of the guys up here, as well as our manufacturing brethren, are looking at how we can get to those energy levels. And it's going to mean architectural as well as device capability. Pardon me?
Is there information on your website?
Probably not on our website, but the DOE has published a report, DARPA published a report on UHPC. Actually, I would go, if you want a report that kind of goes into a lot of detail, go look at the DARPA report on the Ultra HPC project. And it's a big document, so if you can't sleep some nights, that probably will help. Yes, next. Okay.
For the high-speed wire interface, Intel promote both Thunderbolt and USB. So these two standards compete each other or have other focus, application, and usage?
Hickey. I'm proud of you, man.
Well, I was just going to say, maybe Mr. Bhatt is sitting down next to
we should have Ajay.
Ajay answered that one. Yeah. But I mean, for us, the standard is we want to drive to a standard level. The USB is what we've introduced on the mobile platform. It is the preferred mobile standard for us, and we're going to go drive that. Thunderbolt is used inside some of our laptops, but it's for very different purpose in terms of aggregating different interfaces, etc. Those class of devices.
Yeah, we did not architect them to compete. We architect them to address their appropriate segments.
So, Intel's contribution to repro and security features, what can we expect in the future?
Rich?
Well, we continue to extend the feature set of ET to provide support for some of the security features that McAfee offers. And some of these are, if you're familiar with the DeepSafe product, there's things that we're doing in extending the underlying ISA to make that more efficient. So that's one area. The other is that this kind of goes to the question that was asked earlier, how are we dealing with the coexistence issues where you want to do system virtualization as well as provide security, and we do have some technologies that we're looking at, MCS shadowing being one, to address those kind of coexistence issues.
Okay, next question.
This is Shikhar from iGate. Couple of questions. Big data analytics still seems to be the preserve of very deep-pocketed companies. What, if anything, can Intel do, given the proliferation of sensor data that's coming out with each generation, to sort of democratize it across the business world? And secondly, with the success of Samsung and given Intel's immense brand value, is it a time a decade later for Intel to get back into its own branded consumer products?
Mark, I think a nice conversation about our the enabled Hadoop would be a good discussion on big data, don't you think? And what we're doing to enable it?
Yeah, it would. I have to look rightwards to get help with that one, because unfortunately I don't really know a whole lot about it.
And so, we're doing a lot of work with to enable the Hadoop software stack to enable multiple customers, not just the big iron guys, to leverage that framework, not only the file system, but the MapReduce and some of the other extensions that can sit on top of that. We'll continue to do that and provide it to a larger, broader breadth of customers, as well as understanding how workloads emerge with some of the health sciences application, which is a huge big data application, and others. So we're addressing that. As far as marketing, there's a reason we're fellows and not marketing people. We don't make those decisions on what we do. That way we can have plausible deniability. So I'm going to refuse to answer your second question. Sorry.
Steve, I could add just a little bit more, just complementary investment that we're doing in big data. This in the academic side. We have these Intel Science and Technology Centers, one center at CMU, one at MIT, that are doing research in big data and cloud computing in general. And there are systems and frameworks beyond Hadoop that are very interesting for doing big data analytics, in particular those that are based on a graph-based framework. Some problems like PageRank, for example, really is a graph problem. You want to orient your framework around that. And so there's some real interesting work like GraphLab.
However, I will state that you can overlay those on top of the Hadoop framework. You can still leverage the Hadoop file system.
Absolutely. In fact, the two go together, and there's some problems that are more initially expressed as a graph problem, and others that are more as a MapReduce style problem. And Hadoop sort of can encompass both.
And the other focus they're looking at is putting machine learning capabilities into it, because with the volume of data, the machines are going to have to make the majority of the decisions based on some human interaction. Humans just can't scan everything.
Well, there's another factor that we add, that is, you're talking about sensor data. And if you look at a vibration sensor, the sampling rate can be 1,000 hertz up to 20,000 hertz. So the amount of data is just, prohibitive to send all the data to the data center. So actually, that's where we're trying to put analytics on the edge to actually analyze the data, and we set a reduced feature set back to the cloud, and where we do the big data analytics.
Okay, probably have another time for two more questions, and then the David Cantor question. So two more on the data. Next. Not a transistor question. If you do this to me again, I'm going to be so upset. A NAND question?
A manufacturing question.
Oh my God.
Given the accelerated growth in segments of the business characterized by smaller die sizes, does it make sense to rethink your current roadmap and the timing of 450 nanometer wafer transition?
Anybody? Mark, you want to try?
When you say rethink, you mean make it earlier, I assume. No, I think the general comment on our manufacturing is that our fabs are running well at capacity, and we strive always generation over generation to make them more efficient, right, to reduce the cost. And moving to those kinds of technologies or those kinds of feature upgrades are natural for us. We do those. Some of them, like the Monster Visible, are more well known, but we do many of those kinds of feature upgrades per generation. And since we don't see Moore's law stopping, and neither necessarily our volume across the board, we will need to continue pushing for better efficiency in the manufacturing process.
And I really don't see the need to rethink the roadmap when I look at where we're going and what we have. Okay, one more, and then David. David, I'm going to give you like 13 seconds here. So next guy, take your time.
Hi, I have a storage-related question. Given the mobile storage is improving in performance, EMC and UFS is growing in performance, do you see those storage interfaces being adopted in your core platforms? Will it be adopted, and at what time frame if it will be adopted?
So I think the question is, do we expect to see some of the handheld type of storage interfaces like UFS and eMMC be adopted in higher-end segments? Right now, I don't really see that as a driving factor. I think the higher-end segments and lower-end segments have different requirements. The high-end is kind of driven more by voice performance, and the more mobile segments are driven more by adequate performance and power efficiency and so on, compactness and form factor, and so on. I don't see that one's going to displace the other. There are several strata in the market segments, and each has their needs, and they're going to be met not by one turnkey solution that does everything for everybody.
Okay, David, stand up. David Cantor, ladies and gentlemen, give him a hand. You have 29 seconds for question and answer.
All right, so looking at Intel's SoCs, we have a lot of different IP blocks like ISPs, GPUs, and they vary by product segment. So tablets have ISPs, desktops and notebooks don't, and the GPU architecture may vary. How do you guys look at providing a consistent software interface and ecosystem like the x86 architecture, but at the platform level for developers? And hopefully this is a good question.
Actually, time is up. So, anyway, go ahead.
So I'll answer that. For graphics, it's very easy. For graphics, you have the standard interfaces, the DX11 or OpenGL. For the new emerging pieces like ISP, those things don't exist. And we are going to create our own APIs that will hide some of the differences between the different IPs that we bring, because software, as you bring, this learning is the longest pole in the tent in trying to get all of these things out.
It's a great question, David. Thank you. So everybody, thank you for coming. Please give it up to the fellows here in the front. Thank you. We'll see you next year. And by the way, if you have other